Hello, welcome students to this module on motion, and I'm still your instructor, Kayode Babatoke. In this module, we will be dealing with very interesting topics in physics. One, we will be looking at kinematics. Kinematics, we will be looking at the definition shortly. It's the study of motion without regard for the forces causing it. And there are different types of motion. We'll be looking at all of them: translational motion, rotational motion, and oscillatory motion. Then another big section we are going to look at under motion is projectiles. And then the last part, we are going to be dealing with dynamics, where we'll be considering motion together with the forces causing it. And then we'll be dealing with the Newton's laws of motion. This promises to be a very interesting topic. So I want you to give it rapt attention, but I'm going to make my explanation as slow as possible and as detailed as possible. But then, it's not impossible you may not get all you need to get in just one swipe of listening. Anywhere you need to replay again and again, don't hesitate to do it. Because the more time you replay this VCD program, the better will be your understanding of the subject. Now, to the first topic, kinematics. Generally, motion involves the change of position of a body with respect to time, resulting from the application of force. However, in kinematics is the study of motion without considering the forces causing it. And there are basically three types of motion that we will be considering in this tutorial. They are: 1. Translational motion. Translational motion is when a rigid object moves in space without rotating. E.g., when a car moves from one end of a street to another, that is translational motion. When a child moves from one edge of the room to another, that is translational motion. 2. Rotational motion. This involves movement in a circular fashion about a center point, e.g., the moving fan blades of a fan, or talk about the movements of the earth around the sun, or talk about the orbital journey of the moon around the earth. These are rotational motion, or the movement of the wheel of a car during motion. These are all rotational motion. Also, we have oscillatory motion. This is a to and fro kind of motion about a fixed point. E.g., the movement of a pendulum is an oscillatory motion. Another kind of oscillatory motion is, for example, when you attach a coin or a solid object to the edge of an elastic string, and then you give the solid object some displacement. You see that the object will move down and move up and move down and move up. So long as the elastic limits of the spring is not exceeded, there will be a sort of oscillatory motion. So this also is an oscillatory motion. Basically, these are the three types of translational motion that we will be considering under this module on motion. Firstly, translational motion. Definitions. In the definition of a translational motion, 4 parameters are required. These parameters are: 1. The displacement. The displacement is the distance covered in a specified direction and is usually symbolized as S. Displacement. 2 is time. Time is period of flight and is usually symbolized as T. That is the time it takes for this particular displacement or distance to be covered. For example, if a car covers a distance from one end of a street to another, covering a distance of 1 kilometer, that 1 kilometer is the displacement. But if it makes that journey in a space of 1 hour, then the time, which is the period of light, is 1 hour. Also, we talk about velocity. Velocity is the rate of change of displacement with time, that is the s dt, and is usually symbolized as v. In the example we gave earlier, a car that covers a distance of 1 kilometer in a space of 1 hour, then its velocity will be 1 kilometer per hour, because that is the rate of change of displacement with time. That means in every 1 hour, it covers a distance of 1 kilometer. That is the velocity, the rate of change of displacement with time. And lastly, we talk of acceleration, which is the rate of change of velocity with time. So, in the definition of a translational motion, these are the 4 parameters required: displacement, time, velocity, and acceleration. Now we go to a very important aspect of translational motion. We will now look at the equations of motion. Now, if a body having an initial velocity of u accelerates uniformly along a straight line with an acceleration a and covers a distance s at a time t when it reaches a final velocity v, the distance covered is given by the shaded area in the plot below. This is what is called a velocity time graph. It's a plot of the velocity versus time. Because, for example, imagine a car that is just starting from rest. It does not go to, for example, 100 km per hour at once. It goes gradually. Maybe the first 5 seconds, it is doing like 20 km per hour. In the next 10 seconds, it goes to about 50 km per hour. And then after about 60 seconds, it will have reached about 100 km per hour. This rate of change of velocity with time is what is called the acceleration of the body. And when you make a plot of velocity versus time, the total distance covered during the journey is the area under the graph of the velocity time plot. This is a very important point that you need to take note of. If you are given a velocity time plot and you are told to calculate the distance covered within the specified plot, the distance covered is the area under the velocity time graph. For example, in this case, the area of the velocity time graph will be the area of a trapezium. So finding the area of a trapezium will actually give us the total distance covered. But many times, this is because this particular body did not begin from a velocity of 0. If it had begun its journey from rest, that is from a velocity of 0, the area under the shaded portion, that is under the velocity time graph, would have been a triangle, and it would have been easy to find the area by using half base times height. But because the initial velocity is not 0, here we actually have a trapezium. So we have to use half a plus b, that is half sum of the parallel lengths times perpendicular height. I mean, I'm sure you know that, how to find the area of a trapezium. Just to let you know that when you have a velocity time graph, the area under the graph is the distance covered during the journey. In this case, we will be dealing with a trapezium. So the distance covered is half a plus b times h, where h is t2 minus t1, that is times 0. Usually t1 will be 0, minus, that is t2. T2 is the time at the end of the journey, and t1 will usually be 0. And a plus b is the initial velocity as well as the final velocity. So this is what we have: a plus b, where this is the initial velocity, this is the final velocity, and then the height is t2 minus t1. The reference time usually will be 0, like we said earlier. So therefore, distance S will be equal to half into V plus U times T. Let's call that equation 1. Now, if the body begins from rest, then U will be equal to 0, and then S will be equal to S times V times T. That is, U will be equal to 0. Initial velocity will be 0 if the body takes off from rest. Now, for a uniformly accelerated body, acceleration is given by dv dt, which equals to v minus u divided by t, and which is a constant. That is for a uniformly accelerated body. That means that the rate of change of velocity with time is a constant. That is what uniformly accelerated means, and that's why I highlighted this, for me to explain to you what it means, uniform acceleration. Uniform acceleration means the rate of change of velocity with time is constant. Therefore, from this expression, we can make V the subject of the formula and have V equals to U plus AT. This is one of the equations of motion. The first equation of motion is this: S equals to half plus V plus U into T. And the second equation of motion is V equals to U plus AT. Now, if we substitute T in equation 2 for T in equation 1, that is, we still want to use equation 1, but we want to look for another expression to replace T. From equation 2, T will be equal to V minus U over A. So we are going to have S equals to half times V plus U, okay? But then instead of T, we are now going to have V minus U over A. Because from equation 2, if you make T the subject of the formula, you are going to have T equals to V minus U over A. So if we put that here and we simplify this expression, V plus U multiplied by V minus U will give us V squared minus U squared. So by the time we simplify out this expression, we will have 2AS equals to V squared minus U squared. Therefore, if we make V the subject of the formula, we will have V squared equals to U squared plus 2AS. This is the third equation of motion. And lastly, if we substitute V in equation 2 for V in equation 1, we will have V equals to half times. Now, in equation 1, remember we have S equals to half times V plus U times T, okay? And then in equation 2, we have V equals to U plus AT. So what we want to do now is to substitute V from equation 2 and put it here as V in equation 1. So that will give us S equals to half times, instead of V here, we will have U plus AT, then plus U. That is what we are trying to do now. So that will give us S equals to half times U plus AT plus U times T. So if we simplify that, we will have S equals to UT plus half AT squared. I'm sure you can further simplify this yourself to know how we came this far. Because now, to give a little bit of explanation, you can multiply through both sides of the equation by 2. So that gives you 2S is equal to 2UT plus AT squared, because U plus U is 2U. So if you now divide both sides of the equation by 2, you will now return back to S equals to 2UT over 2. That gives you UT plus AT squared over 2. That is half at squared. So this is the fourth equation of motion. Now we have generated 4 equations of motion which we are going to be using in dealing with problems relating translational motion. Now, the equations of motion are summarized below. 1. S equals to half into u plus v times t, where u is the initial velocity, v is the final velocity, and t is the time of light. So you can use this equation to calculate S when you know the initial, final velocity as well as the time of light. Equation 2, v equals to u plus at. You can use this equation to calculate velocity, final velocity, when you know the initial velocity, the acceleration, and the time of light. The third equation is v squared equals to u squared plus 2as. The fourth equation is s equals to ut plus half at squared. These are your tools of work relating answering questions on translational motion. And you have to use these equations as often as possible to ensure that they become a part of you, or as well you have to memorize them, because these are your tools of work. Even if you can't derive them, you should memorize them. But I think I've been able to show you how to derive them earlier. By just replacing certain terms with certain other terms, you find out that you're able to generate a new equation. Now, how do you know which equations to use when confronted with a given question? That I will be explaining as we go into the examples. As we move on, I will show you how to know which of these equations you are supposed to use in solving particular problems. Now, some important points you should know about units of the parameters that define translational motion. You still remember that we said translational motion is defined by 4 parameters: acceleration, velocity, distance, and time. In SI units, acceleration is measured in meters per second squared. Velocity is measured in meters per second. Distance is measured in meters, and time is measured in seconds. But on the field, for field units and for practical purposes, acceleration is measured in kilometer per hour squared, velocity in kilometer per hour, distance in kilometer, and time in hours. So it now becomes very necessary for you to be able to make conversions, because when you are solving problems, you have to ensure that your parameters are in a consistent set of units. When you are using any equation of motion, you have to ensure that all of these parameters are either in the SI unit or all in the field unit. You cannot mix SI unit with field units. Your answers will not be correct. So you either work in SI unit or you work in field unit. So some important conversion factors you may need to know is this: that 1 meter per second is equal to 3.6 kilometers per hour. So when you are given velocity in kilometer per hour and you feel like working in SI units, you should know that 3.6 kilometers per hour is equivalent to 1 meter per second. So it is 1 meter per second that you will use in your equation. Based on this, you can calculate also the value of any other kilometer per hour. For example, 36 kilometers per hour will be equal to 36 divided by 3.6. That gives 10 meters per second. Also, I expect anyway that you should be familiar with this, that 1 kilometer is equal to 100 meters. So if you are given a distance of 1 kilometer and you intend to work in SI units, it is 1,000 meters that you will put in your equation, and also that 60 seconds equals to 1 hour. The following are certain notes on how to use the equations of motion. Now, the first point is this: a maximum of 5 variables are involved in any translational motion problem: acceleration, final velocity, initial velocity, displacement, and time. You know, there are actually 4 parameters, but why we now have 5 variables is that in terms of velocity, we can have an initial velocity which is different from the final velocity because of acceleration. So both v and u are velocities, but v is the final velocity while u is the initial velocity. So how do you know which equation to use? Choose an equation which contains the variable you are told to calculate and does not include the variables that you are not given. Okay, for example, a car moves from rest. This indication of a car moves from rest already tells you that initial velocity is 0 with an acceleration of 0.2 meters per second squared. Find its velocity when it has moved a distance of 50 meters. Now, check out the way I'm going to progress. We said that there are 5 variables that are involved in any equation of translational motion. Maximum of 5 variables. But not all the equations have all of the variables. For example, in green are the variables that we are given. We are given acceleration, we are given initial velocity, and we are given the displacement in this question. That's why I put it in green. That's green lights. You are given those ones. But then, you are not given time. Nothing relates to time here. And you are told to find velocity. So, the way to know which equation to use is you will look for an equation which contains velocity but which does not contain time. Because if it contains time, you won't be able to solve it because you don't know the time. But then you have to use an equation that contains the parameter you want. In this case, your choice will be v squared equals to u squared plus 2as. Now, how did I come to that? Let's see how we made the choice. You cannot use equation 1 because even though they gave us time, they gave us initial velocity, yes, we are looking for final velocity, and they didn't give us time. So there will be 2 unknowns in this equation, so you can use it. What about equation 2? We are given initial velocity, we are given acceleration, but we are looking for final velocity, so we don't know it, and we are not given time. So you can't use equation 2 because there will be 2 unknowns. What about equation 3? You can't use equation 3 because it does not even contain velocity. We are supposed to calculate final velocity, and final velocity does not even show up in this equation, so you can't use it. Secondly, if final velocity showed up, time is in this equation and you don't know the value of time, so this equation is inadequate. However, equation 3 meets our need because you want to calculate the final velocity, fine. We have been given the initial velocity. How did we know that? Because we are told that the body starts from rest. That means initial velocity is 0. We have been given acceleration at 0.2 meters per second squared, and then we have been given the displacement to be 50 meters. So, equation 3 is our choice of equation to use. V squared equals u squared plus 2as. So v squared equals to 0 squared, remember, because the body is beginning from rest. Initial velocity is 0. Then 2 times acceleration times 50. One more point you need to check out is that you are working in a consistent set of units, which is the case here. Acceleration is in SI units, and then your distance is in SI units. So that's good. You are in a consistent set of units. So here we have v squared equals to 20, and we have v equals to square root of 20, which is approximately 4.47 meters per second.